what I want to talk about is also basically an extended abstract of a paper that was presented at XLoKR. And this was joint work with Koopman, who did this as part of her MSc thesis project. First, I'll give you the context and the motivation for what we originally started out to define these kind of explanations, which we call persuasive contrastive explanations. But you will see that there are a number of things and concepts that you will recognize and have also seen before today in various similar versions of it. Then I'll introduce what we call an explanation. Lattice is what we use to compute these kind of explanations, and end with some conclusions. So the context in which we started out this research was explanation of Bayesian networks. And I was teaching a course on this, and then I basically discussed that in general. You could say there are three kinds of explanation that is distinguished in the literature. It's first the explanation of a model, for example, just by showing the graph, where I've shown an example graph right here. This is an existing Bayesian network called the child network, which is meant to diagnose congenital heart disease in small children. You could also explain evidence. So I've got a set of observations. What is the set of non-observed variables that is most likely under these observations? And but most often things are about the explanation of the reasoning, and we've got very different types of approaches for that. But usually what they aim to do is to justify the obtained outcomes. And with an obtained outcome, I basically mean a prediction for an outcome variable of interest, and a prediction is in a Bayesian network of distribution. So in this case, the disease variable is what we're interested in. So our outcome for a specific patient, where the characteristics of the patient are modeled by the observed evidence E, and in the graph you can see that those are the red bars in the histograms that indicate that that is observed with certainty right now. And the outcome is a prediction, so a posterior distribution over our outcome variable. And in this case, one of the 6 different possible values is the most likely one, with almost 80% probability. Note also from this example that I'm not making any assumptions about variables being binary values. So the outcome here has 6 different values, but you can also see that some of the input variables have 3 or 5 different values. So, well, as I said, this was joint work with Tara. So she followed my course and she said, okay, I want to do something with explanation in Bayesian networks. So what can I do? So I said, well, have a look at what has been done, but also have a look at what is being done in machine learning research, because they're doing things that we have not been doing in the context of Bayesian networks. And one of the things that was very clear was that a lot of explanations in machine learning research use counterfactuals to answer contrastive questions, and up to that moment we weren't doing that in the Bayesian network community. So a contrastive question, and this was mentioned already before today, is basically you want to answer the question, okay, I'm getting output T, why am I not getting another output? And in this case, I'm assuming that the user expects some output T prime, where the system returns output T. And I'm also assuming that this is a targeted question. So I'm not asking, why aren't I getting some other output? I'm specifically asking about, why don't I get T prime? Of course, in a binary output variable, that would be the same question, but in general, it's not. And also, there are lots of different definitions of what counterfactuals are. And in this case, as is often done in machine learning research, it's just what change in input is required if I want to change my outcome to some other value. So what I'm not talking about is causality. I'm not talking about intervention. So all my input are observations, not necessarily the result of interventions. All my outputs are predictions. So I'm not trying to find a cause for something I have observed. And as I said, the question is targeted. So I'm looking for an explanation specifically or counterfactual specifically for an output value t prime different from t. So it was already a while ago, December 2019, that Tara decided to use these counterfactuals to explain Bayesian networks. In the meantime, we have seen similar concepts also in the context of Bayesian networks, and even where we'll propose to combine two types of explanation. We have seen similar combinations, not directly in the context of Bayesian networks, but in other contexts as well. So because we're looking at Bayesian networks, and as I said, our output is a posterior distribution. So what does an outcome mean? Well, in that case, we're reducing that to what is the most likely one. So the outcome is the most likely one predicted by the network. And an answer to this question, we thought, was one that on the one hand should persuade the user that in fact the output t that the model is given is the correct outcome, so is the correct prediction for the observed input. And on the other hand, should also provide alternative contexts in which t prime would be returned. And with a context, in this case, I mean another combination of values for those variables that are observed. So I've got evidence for a number of here, for example, I've got these 4 variables that have evidence. There are other variables that are also observable, but I don't have evidence for those. So focusing on these 4, what other values of these would result in the output that I'm interested in? Okay, so we call this combination a persuasive contrastive explanation. So on the one hand, it should persuade the user that what we find is the correct output. And we do that by giving a sufficient explanation, which we define as the minimal subconfiguration of the evidence, the observations that we actually have, that would already suffice to conclude the current output, regardless of the other values for the observed variables. And this is very similar in definition also to what, and also already in the context of binary Bayesian network classifiers, we've seen this under different names. For example, the prime implicant explanation has the same definition. And as the name already suggests, this was inspired by the prime implicance from logic. And the other part, the counterfactual explanation, is a minimal subconfiguration of the unobserved values for the observed variables. So it's the other values for these variables other than we have actually observed, in combination with the values for the observed variables that we have observed. So if I change a subset of those observed variables to a different value, that would give me the targeted output t prime. Okay, so there's something about how to compute them, or an observation about what the complexity of that would be. First of all, if we look at how many potential sufficient explanations there are, that if we look at the search space of all the possible outcomes. So the number of potential sufficient explanations is exponential in the number of observed variables. And the number of potential counterfactual explanations is actually as big as the number of combinations of observations we could have had for those variables. So that is worse unless you have binary valued variables. In that case, it would be the same. And in the context of Bayesian networks, that means we have to compute the output of the network for all those combinations of value assignments. That means doing probabilistic inference, which is NP hard, and we need to do it an exponential number of times. So we thought, okay, let's see if we can find an algorithm that does that more efficiently, hopefully, than the worst case possible scenario. And well, we've decided, looked at various properties, and these are in the original XLoKR paper. that allow us to compute that using a basically a breadth first search or a combination of breadth first search, which we now call the BFS for breadth first search for sufficient explanations and counterfactual explanations. And we do that search on a subset lattice. So basically that structures our search space, which we annotate dynamically while we're searching for the explanations and doing the computations. So let me explain what that explanation lattice entails. Well, as I said, it's a subset lattice. So what we have is the set of variables for which we have observations. So in this case, suppose that's X, Y, Z. And we annotate it basically with three things. The first one is the combination of values for these variables that we have actually observed. And we do that for every subset. So suppose my current evidence is X1, Y1, Z1. So for the top lattice element, that is the combination I get. And then, for example, if I go to the subset XZ, then X1, Z1, again, the observed values would be the potentially sufficient explanation for that lattice element. So that means if we want to look for the smallest sufficient explanation, we go from top to bottom through the lattice and to see if those associated explanations are actually sufficient explanations. Another thing we annotate the lattice with is all pairs of C and T star here, where C is a combination of values for the complement of the variables that are mentioned in the subset lattice. And it is a combination of values that is not observed. So again, if I look, for example, at the subset XY, then Z is missing here. So I'm interested in value combinations for Z that are not observed. Well, recall that we had observed Z1. So in this case, C2 and C3, I'm assuming this is a ternary variable, are not observed. So these are the pairs that I listed here, and each will have some outcome for the variable of interest in combination with the observed values X1, Y1. And that combination I need to compute. So for that, I need to do inference. And because I only want to do inference for all those combinations where I really need to do that, I start out labeling all these with the outcome is unknown. And only when I really need to do the computations, then I do the computation and establish the outcome. Well, all these pairs basically represent the potential counterfactual explanations. And the third thing that we annotate the lattice is if we have computed all the outcomes for those possibly counterfactual explanations, in order to know if they can be counterfactuals and also to know if we need to continue searching, we again define three different labels. And again, until we do the computations, these labels are empty. The first label is a label true. That means that all the outcomes, for all the possible outcomes, so for all possible combinations of the evidence other than we have observed for the variables that are not in that lattice element, we find the same outcome that we had in the first place, so our original output. So that means that regardless of the values for variables in C, we will find output, our original output. So that means there could be a sufficient explanation there, but there still could be a smaller one. And so that means, for example, if I think there's potentially a sufficient explanation X1, Y1, then I need to continue my search, because if X1 is a sufficient explanation by itself, that would be a minimal or a smaller one. So that would be the one I was seeking. So if I find true, that means I should continue searching for sufficient explanations. And if I find another label, So that means that either all of them are the alternative output I'm looking for, or it's some mixture of the current output, the one I'm looking for, and perhaps even another one. Then I can, depending on the situation, continue searching for counterfactual explanations, but I can also know that I can stop searching for sufficient explanations. So if they're no longer all resulting in our current output, I don't have to continue searching for a sufficient explanation. And if I know that all of them are the targeted alternative output, I know I can stop searching from there on for counterfactual explanations, because the higher up I am in the lattice, the smaller the set is for the counterfactual explanations, and I'm again looking for a minimal set. So going further down only means that the C becomes larger. If I find a mixture, then, well, I know there's no longer a sufficient explanation if I go further down, but there could still be counterfactual explanations. So I need to continue there, unless my output variable is binary, because then the only alternative is the T prime. So just to give you an example of how this works. So again, I have this child network, and as I said, I have two binary inputs, but two non-binary inputs, and I have a non-binary output variable. My current most likely outcome was the PAI-VS right here, and suppose that the user had expected this rather unlikely outcome, TGA. So these are all congenital diseases. These four different input variables, I've labeled them with HOCX, which is related to the names they have, but that's not very important right now. So these four variables give me this subset lattice right here, and I'm going to show you how to go through that lattice. So of course I start at the top, and that was the combination of values that I had originally observed, and I know that it's going to give me outcome T. So basically I immediately continue to the children in this lattice, and I start computing the outcome for all the combinations with unobserved values for the ones that are missing here. So in the left one here, X is missing, so I'm computing the outcomes for all combinations with other values of variable X, which were for the four different ones in this case. So in the brackets here, you see the number of computations we need to do. That has to do with the number of possible combinations of other values other than the ones observed for the variable missing from the subset here. And in front, we see the number that we actually do compute. In this case, these are all the same, but we will see later on that will differ. And the label here is as I explained. So here I find other, so I find a mixture of different possible outcomes. And in this case, I in fact find the targeted outcome that I'm looking for. So that is a counterfactual explanation potentially. And for that reason, I also enqueue this variable or this element into a separate queue in which we will search for the counterfactual explanations. And for the rightmost one, that same holds. In this case, none was linked to the T prime that I'm looking for. So these are all other than the T and the T prime. But again, I can continue to search for counterfactuals there. So that is also enqueued in that other queue. The two in the center here, we see that all possible combinations of other values for the variable missing from this subset still give me the same outcome I had before. So these could potentially be sufficient, but I could possibly have smaller sets, so I continue the search there. And then in this case, this is the smallest one I find that still results in the same target, same output I had originally. And that means that here I have a sufficient explanation. So these were the original value, observed value of h, and the original observed value of x. And that is a sufficient explanation. In this case, the only one I find. So recall that in the meantime, so now I stopped the search for sufficient explanations. In the meantime, I had basically initialized another queue for the counterfactual explanations. So I continue my breadth first search from there. And well, we do similar things, all the computations. And now you see, but because I have one counterfactual explanation here for one of the values of x, I no longer have to invest computations where I include that value of x, because further down in the lattice, any combination that includes that value of x, I already have a smaller counterfactual explanation. So here you see that I no longer need to do the maximum amount of computations as I go further down in the lattice. Here I find another counterfactual explanation, and again I go all the way down, and in this case all the way down to the bottom of the lattice. That's not always necessary, and especially when all the variables are binary valued, I typically stop much higher up in the lattice, and I don't have to continue all the way down. So in this case, I find 4 different counterfactual explanations for 3 of these lattice elements. So I have one here with a value of x that is different from observed. I have one here with values of, or 2 here, I should say, with 2 different combinations of values for x and h. And I have one here for a combination of values for x, h, and o. So what I try to illustrate is that the size of the lattice is determined by a number of input variables, and we have to search through this lattice. So that is one of the aspects of the computational complexity. Then we have the number of computations we really have to do within the lattice. Depends on the number of input configurations. So and those computations are the ones we do in the Bayesian network. But in essence, if you see what we do with the breadth first search through the lattice, that doesn't depend, and neither do our definitions of sufficient and counterfactual explanation, do not depend on the fact that we are using a Bayesian network. So what I presented here is, in essence, is model agnostic. And you could use the same, as long as you have inputs and you know how to determine an output from that, you can use any underlying model there and do the same procedure. Well, in the example, we covered the entire lattice from top to bottom. That is not necessarily always the case. And there are further optimizations possible. Some could be domain specific. For example, we can use monotonicity properties if we know that higher ordered input values, for example, result in higher ordered output values. I can say, okay, I'll just check the lower for counterfactual, the lowest ordered value. And if I'm interested in an alternative output that is lower ordered than my current one, I don't have to look at any other possible combinations that are higher ordered, because I know I won't end up in a lower ordered output. So that also means that you can use information like that to prune the search space. So either pruning the lattice itself or the number of configurations we need to check in the lattice. And another thing is that you could do anytime you do a call to the model that you're trying to explain, in our case, a Bayesian network, you can try to do model-specific optimizations to the computations you need to do. And in the context of a Bayesian network, we could, for example, use saturated junction trees to speed up the inference. So to conclude, we introduced persuasive contrastive explanations, which at the time of introduction were original, at least for Bayesian networks. And originally, we introduced these for Bayesian networks, but in the end, it turns out that what we do does not really depend on the fact that we have a Bayesian network. The complexity depends on both the size of the lattice and the cost of model inference, whatever model you're using. But that in practice often will mean, I guess, that it's suitable only for low dimensional input spaces. So for future research, what we would like to do is to look at counterfactuals beyond the observed variables. So now we've restricted only to other values of those variables that we have observed, whereas, for example, in the network, there were other variables that are also observable. We just did not have an observation for them. Also to look at the role of causality, because it's especially clear today that when you talk about interventions, things work differently than when we just have observations. In the example here, we had only one possible sufficient explanation. We had 3 or 4 counterfactual explanations, but in practice, that number of explanations can become very large. So we need a way to select which ones to present to the user, and that may also depend on preferences of the user. And then also, how do we present these to the user? So not in math notation, but, well, what way can we convey this information that makes it understandable to human users? Thank you.